Hi, my name is Natalie Kerr, and this is my H-NMR and C-NMR analysis of the molecule succinamide. So NMR is all about the magnetic fields of different nuclei, and it's a great way to figure out the purity of different isomers and the different bonds or arrangements within a molecule. In this case, we know that we're working with succinamide, but we'll pretend that we don't know that. Proton NMR, or H-NMR, looks at hydrogen nuclei specifically. Each molecule has different regions for carbons and hydrogens, and NMR-DB is a really good site to use as a tool to help you determine how many of them there are. And the number of peaks on the graphs corresponds to the different regions, so this is something you want to pay attention to. If you go to the site and you put in your molecule, here on the right, then it'll blow it up and show where the hydrogens are attached. These 4 hydrogens on the bottom of the molecule all correspond to the same section, and then this one on the top is its own little deal. If we look back at our graph, we can see that over on the left we have this little blip, and that is caused from the amide on the molecule. And the reason it appears so lightly and all the way at about 8.7 is because nitrogen is a very electronegative atom, and it deshields the hydrogen, which causes it to downshift. So the peak appears downfield of where we would expect it to be. We can compare this and the peak over here at about 2.7 to a handy chart from Compound Chem, where we match it up and we see that our 2.7 molecule could be an alcohol or an acetylenic or something like that, and those are our first glance options. But when we account for this amide and the downshift that we saw happen in that, we have to account for downshift in our other spike, which means that we're actually dealing with this ketone right here. C-NMR, or carbon-13 NMR, operates on the same principles of H-NMR, where it sort of measures the magnetic fields of nuclei, but this time it uses the C13 nuclei. If we look at this C-NMR graph, we see 2 peaks, which correspond to the 2 regions of carbon atoms that we can see in the NMR-DB analysis. And each peak has this little prefix of 2, and they correspond to these 2 carbons and these 2 carbons. And because we're dealing with a symmetrical molecule, that's why they're going to be the same and they're going to be the same. And then when we go and look at our compound chem sheet, we can see that the first amide does match up with the peak. Furthest to the left, we see our amide here, and it shows up in roughly the same place. And then the other peak is most likely some kind of alkyl. It could really be any of these because it overlaps. So this is why it's good to pair it with H-NMR, because it can be difficult to get all of the information from just one of the graphs. We also need to use the N+1 rule to look at splitting in the number of adjacent hydrogens. This allows us to check ourselves and to know for sure if we have the right combination of atoms in our molecule and that we've arranged them to be the right substituents. Our molecule has the chemical formula C4H5NO2. And we know that there are 2 zones of hydrogen and 2 zones of carbon. So when you look at this, you take a carbon and then you look at the adjoining carbon and you count how many hydrogens are coming off of it, and then you add that +1. And so for each of these, we get 2, which is what matches up to those spikes that we saw before, which confirms that we are correct with our assumption of ketones and amides being present in this molecule. When we add all of this together, we get this molecule, which is our succinamide, and we have our symmetry, we have 2 ketones, we have an amide, we have 2 zones of carbon and 2 zones of hydrogen, and that's our molecule.